In this video, we are going to look at the ideal inverter. We are going to think, what is the inverter that gives us everything that we want? This is the benchmark against which we will measure everything else. The second thing we will do is to look at an important tool for the characterization of logic families, specifically their static behavior, which is the voltage transfer characteristic. So if we consider an ideal inverter, an inverter that gives us everything we want, so let's try to visualize how the output voltage of this ideal inverter changes as its input voltage changes. So if we give this inverter a voltage of 0 volt at the input, we expect it to give us the highest potential it could at the output, which is VDD. And also, if we give it a voltage of VDD, we expect it to give us the lowest voltage possible at the output, which is 0. And so these 2 points, 0 and VDD and 0, they must lie on this curve somehow, right? And why are we asking this ideal inverter to give us VDD and 0 volt as outputs? Because this increases the difference between the clean 0 output and the clean 1 output. So if we assume that this is a clean 1 output and this is a clean 0 output, this increases the difference between them. And if it increases the difference between them, it will potentially give us more margin for noise to affect us without changing the value of the logic. So the other thing is, if the input changes a little bit, if it is not 0 volt as an input, but it's a little bit higher than 0 volt, then what happens? If the input is not 0 volt, but a 0 volt plus some kind of noise, we still want the output to be VDD. We want to be resistant to noise. And if the input is not VDD exactly, but a little bit lower because some noise has subtracted from it, we still want the output to be 0 volt. We still want the inverter to recognize this as a logic input and give us the correct and full logic output at the output, meaning that it has completely cleaned all the noise. So this is going to continue to be 0 going down, and this is going to continue to be 1 going up, and then they have to meet somewhere in the middle, and there has to be a transition between the two. And so the transition is going to be in a brick shape like this, and there's going to be a very sharp drop at some point in the middle. This point is called VM. So if we assume that there is, the noise that affects a logic 0 input has the same average power as the noise that affects a logic 1 input, then it makes sense to make this point, this VM, VDD over 2. It makes sense to make it halfway between VDD and 0 volt, right? So more systematically now, let's assume that this inverter gives a logic 1 output, which is equal to VDD. This is the clean logic 1 output. At the input of the next inverter, what is the amount of noise that we can add or subtract from this logic 1 output of the first inverter and have the second inverter still recognize this as a logic 1? That is to say, what is the range of inputs for the second inverter that it sees as a logic 1? If we look at this curve, then this whole range from VDD to VDD over 2, this whole range is recognized as a logic 1 input by the second inverter. The reason we say that is that the second inverter produces a 0 volt in response to this entire range. And so this entire range, on the other hand, is seen as a logic 0 input by the second inverter. And so these are the noise margins that we have been talking about, right? So the range between VDD and 0 volt is divided in half, or at least is divided completely between logic 1 input and logic 0 input. And therefore, we are using every single point on the voltage scale as a useful input. Now, this is the ideal inverter, but a realistic inverter is not going to have a VTC that looks like this. The VTC of a realistic inverter is still going to be monotonically decreasing. That is to say, it's going to look something like this. It's going to decrease continuously, but it's not going to be a brick shape like the ideal inverter. So what is the difference between this realistic inverter and the ideal inverter? To understand the difference, we want to understand a bunch of really important points on this curve. The curve that draws V output on the y-axis and V input on the x-axis is called the voltage transfer characteristics, VTC, and it is the most comprehensive and most important description of the static behavior of an inverter. So it is the best way to describe how the inverter behaves when its inputs are stable for a long time. So now let's assume that this input is giving us a clean logic 1 at the output. What is the voltage level corresponding to this clean logic 1? So what is the voltage level corresponding to logic 1 at the output? We call this V output high. Similarly, a clean logic 0 is equal to V output low. For the ideal inverter, V output high and V output low were VDD and 0 respectively. For a realistic inverter, this is not necessarily the case. In fact, V output high could be lower than VDD and V output low could be higher than 0 volt, right? So, but how are they defined? So V output high is a clean logic 1. So it comes in response to a clean logic 0. But what's a clean logic 0 at the input? One of the most important principles we have to assume is that the input to a logic gate has to come from a logic gate from the same family. And so if we want to find V output high at the output of the second inverter, we should find it with an input of V output low to the second inverter. Because what is the cleanest logic 0 that could happen at its input? It's V output low, because it's going to come from a similar gate. So it's not going to be better than V output low. So basically, we go and apply an input of V output low, and we find what the corresponding output is, and that's V output high. And so this point, V output low and V output high, lies on the VTC. Similarly, V output high is the output when the input is V output low. So we input V output low, when the input is V output high, the output is V output low. So we input V output high, and we get the value of V output low at the output. And this point, V output high and V output low, is also on the VTC, on the curve, right? Ideally, V output high should be VDD and V output low should be 0, but that's not happening here, right? Another important point on the VTC is the point where input is equal to output. So the curve is dropping, right? There's a point somewhere here where the input and the output are equal. We can find it by drawing the line V output equals V input, Y equals X, and wherever it intersects the curve, this is the point where V output is equal to V input. So this point is called Vm. This is the point that was VDD over 2 in the ideal inverter. Vm is called the logic threshold or inverter threshold, and it should be distinguished from in the transistor threshold voltages, V threshold. So logic threshold is usually a relatively large number. It lies somewhere in the middle between VDD and ground, and it is the point at which the input and the output are equal. What does it distinguish? What does it signify? Any input that is larger than Vm will produce an output that is smaller than it. And any input that is smaller than Vm is going to produce an output that is greater than it. So if somebody holds a gun to your head and says, what is the point on the VTC that represents the transition from input 0 to input 1, it would have to be Vm, although we will define true noise margins more solidly shortly. There are two other points that are really important on the curve, and they are the points at which the slope of the curve is -1. So as you can see, the curve begins with a range in which the slope is less than 1. And when we talk about slope here, we are talking about the absolute value, and ends in a range in which the slope is also less than -1. And then in the middle, there is a range where there is an absolute slope that is greater than 1. We call this the high gain region. There are 2 points of inflection between that delimit the high gain region at either side. And so they are the points at which the slope is barely -1. We are particularly interested in the input values at these points. So the lower of them is called V input low, the higher of them is called V input high, right? And so these 2 points, they they bound between them a region in which the curve has a slope greater than 1, right? And so they divide the curve into 3 ranges: a range before V input low, a range above V input high, and a range between them. This range below V input low actually is a valid logic 0 input. This range above V input high is a valid logic 1 input. And the range in between, this whole range, is a wasted transition region. We should not use inputs in this transition region. In module 13, we'll talk more about why this transition region should be avoided. But in short, the sensitivity of the output to the input in this range is very high because the slope is high. So a small change in input will cause a very high change in output. So we are very sensitive to noise, and we want to avoid these ranges and go to the stable ranges. So the question now, if the clean output, logic 0 output, is V output low, are we worried about noise that subtracts from this noise? No, because noise that subtracts from it is going to make it smaller, and that's good for the upcoming gate. We're worried about noise that adds to it. So how much noise can we add to it before we can no longer consider it to be logic 0? As much noise as takes us to V input low. And so the difference between V input low and V output low is noise margin low. Similarly, at the current gate, the clean logic 1 output is V output high. Fine, this is fine. But what if there is noise? If the noise is adding to V output high, that's okay. But if it is subtracting from it, then how much noise can we tolerate before we no longer recognize this input as a logic 1? And the answer is the difference between V output high and V input high. And we call this noise margin high. And so what's happening here is that there are 2 voltages, V input high and V input low. And the difference between these 2 is noise margin low, and these 2 is noise margin high. And so if we compare the ranges to those of the ideal inverter, we find that the non-ideal inverter is wasting headroom above the output high and headroom below the output low and the transition region in the middle. Whereas in the ideal inverter, the entire range was divided between the noise margins. So if a gate is to be good, it should resemble the ideal inverter. And the way it should do that is by giving us a V output high that is close or maybe ideally at VDD, and V output low that is at 0 volt, and a transition region that is as small as possible, returning us to the original noise margins and to the original robustness.